Hello students, today we are going to see the new concept in electrostatistics, that is the unit 2 is work and energy. This work and energy concept is base for your potential energy and your equipotential surfaces. So what is a work and what is energy and how it is applicable in our electrostatistics? Let us see. If a charged body is placed in an electric field, the force will be experienced by it. What it means? For example, consider these are all the electric field lines. So in these lines, these are all the electric field lines. So this is the direction of your electric field lines. For example, if I place a charged body, something like if I place a Q in this field, what happens? This charged body or this charge will experience some force. This Q will experience some force due to this electric field. That force will be in this direction. The force experienced by the Q will be in this direction. That force is equal to F bar. What happens? By experiencing this force F, this body or this charged body moves in the direction of F or moves in this direction. Because of this field, this Q will move in this direction because of this electric field. So by using for example, this is a point of A. By using some external force, if I move this body, or if I want to move this body to the original position, for example, what happened? Actually, it is in the position of A. Because of this electric field, this Q may move to this position. This is your new position, this is your old position. So by using some external source, we need to apply some force in opposite direction to move the body to its original position. It means that we need to do some work. So in this movement we need to expend, or we need to expend some energy in the movement of this charge from new position to the old position. And take one more example. If the charge body is at this position, if I want to move the charge body to a point of C, that is in the opposite direction of your electric field, again in this position also, in this situation also, we need to expend, or we need to do some work. For that work we need to expend some energy in the movement of the charge from one position to another position. So we have to do some work. That work is done when the charge is displaced from one position to another position by an external source. So to do this work, we need to expend some energy. This expended energy is converted into field energy and it is stored in the form of potential energy. So what do you mean by potential energy? The potential energy is nothing but it is the energy expended in the movement of a charge from one position to another position in the electric field. Take one more example. For example, this is a charge Q. And the field lines due to this charges, for example, this is considered, these are all the field lines due to this charge Q. Let us consider one more charge, that is this is your Q1, this is your Q2. I have placed my Q2 charge in the field lines of Q1. At this point I have placed. So because of these electric field lines, these Q2 will experience some force. The force direction will be in this direction. Because of this force, this Q2 may move in this direction. So if you want to make that Q2 to, or if you want to move that Q2 to its original position, we have to apply some opposite force. In this process we need to expend some energy. that energy will be stored in the form of potential energy. So the potential energy is nothing but the energy which is expended in the movement of a charge from one position to the another position in the electric field. So for example, so this is your original position. Let us consider this is the distance. I have, for example, I have moved my this Q2 to this position. This is your new position. For example, if Q2 is in this position, then the distance will be d1. So what happens? The force is inversely proportional to the d square. Always the force is inversely proportional to the d square. If distance decreases, the force will increases. So here we need to derive expression for this potential energy or work done. So let us consider the force on. So let us consider a field lines of like this. Field lines of like this, and the electric field is in this direction. I have moved from a charge from P1 to P2. The direction will be, the path will be a random path. This is from P1 and this is a P2. I have moved my Q1. This is your Q1 charge. I have moved from P1 to P2. This P1 is initial position and P2 is final position. Let us take some point over here. So this is your DL, and the direction of your E will be in this direction. Then the force also, the force expended or the force on the charge will be in the same direction. So at this point, if I want to consider the energy which is stored or the work done in the moment of from P1 to P, the force written, for example, consider this is a point of V, middle point P. So force on charge, if the charge is moved from P1 to P, if our movement is from P1 to P2, but in the middle point we are considering the charge is at P. If the charge is at P, then this charge will experience some force at a point P. We are considering some infinitesimal distance. Then the force on charge at P becomes force on charge at P. P is nothing but it is a point in between P1 and P2. It may be a middle point or it may be any point. So we are considering force on charge at P becomes the force is equal to F dash is equal to force on P. So force is equal to E and field intensity, that is your electric field, that is your E. Then the differential work done in movement of charge from one point to another point, that is minus Q minus Q E dot dl. Why it is negative? Because we are doing some work in opposite direction of your electric field. This negative indicates we are supplying some force by using some external source in opposite direction of your electric field. So this negative symbol indicates that one. So from this we can write work done is equal to minus P1 to P2 Q electric field, and this is your differential length E dot dl. Here you may get two types of work, that is positive work. The work may be positive, the work may be negative. What do you mean by if work is equal to positive? It is nothing but the energy. If work is equal to positive, that indicates that energy is transferred from source to field, from source to If work is equal to negative, this is nothing but field is supplying energy to move the charge. That we can write it as, in this case, field is supplying energy. If W is equal to negative, nothing but electric field is supplying energy to move. Energy to move. That is, if Q1 is here, so these are all the field lines. If Q2 is here, so because of these field lines, this Q1 will experience some force. So because of this force, this Q2 will move in this direction. In this condition, the W becomes negative. But if you want to move that Q2 to the original position, we have to apply some force. In that situation, we have to do some work. In this position, the work will be positive. So at this situation, we have to supply externally. We have to supply some force or energy externally. So work done in moving a point charge in the field of another point charge as following properties. So these are all some properties when a point charge is moved in the field of another point charge. What are the properties? Work done depends only on the initial and final positions of Q dash in the field of Q, and it does not depend upon the shape of the path taken. For this one, let us take one example. The first point is, work done depends upon only on the initial final positions of Q dash in the field of Q, and it does not depend on shape of path taken by the charge. For this, let us take one example. Find the work done. Find the work done in moving a point charge Q dash from P1 to P2 against electric field Q. Against electric field Q. What would mean? For example, if Q is a charge, with this we are going to get some electric field. So Q is a one charge, and if I move a Q dash from P1 to P2, the Q dash is at this point, Q dash. If I move from P1 to P2, from Q, let us consider the distance is R1. From this point, the distance is, let us consider R2. The direction of field lines will be in this direction. The direction of your field lines will be in this direction. So here the distance is, let us consider this is your distance of R. So in this we are moving, in this path we are moving your Q dash. So let us consider the unit vector in this direction is AR. Then electric field is equal to, electric field intensity is equal to, E is equal to electric field intensity due to this Q. So Q by 4 pi epsilon R square, that is your distance, and your unit vector. Already we have seen what is electric field intensity. So according to the work done equation, work done is equal to minus Q dash. We are moving Q dash from P1 to P2. So minus Q dash integral over P1 to P2 P2 E dot dl. But what is E? Minus Q dash P1 to P2 Q by 4 pi epsilon R square. AR is a unit vector and dl is differential length vector. So for this we can write minus, here P1 is nothing but this is your P1 to P2. What is a P1? P1 is nothing but your R1. So integration over R1 to R2 Q1 Q by 4 pi epsilon R square. So while considering a concept of differential length, we have considered some 3 coordinate systems, that is of x, y, z. So in the differential length, you may have something like dl is equal to, we got something like ax in the direction of your ax plus some ay in the direction of your ay and az in the direction of your az. So this is one coordinate. Here you can consider this is a one more coordinate and 3 coordinate system you can consider. So here you are having, this is your AR. AR is a one that is your unit vector which is defined in the direction of your electric field. This is one coordinate. So in the 3-dimensional coordinate, the 3 coordinates are orthogonal to each other. If I multiply this AR with, so one of this XYZ, one of this one is AR, because this is your, we are considering this is your X. Here AR and AR becomes your AR dot AR equal to 1, you will get. So this totally can be replaced with dr. That is your differential length on this axis. So this is a point. So this is your AR. So we are considering some point over here. This is your differential R. So this is a point of dr. So Q1 into Q by 4 pi epsilon into R square into dr. So this becomes your, this is a dr is nothing but some value R. This is totally the length of R. Some point R, some length on this R. So dr is equal to, what are you going to get here? So minus Q1 Q by 4 pi epsilon integration over R1 to R2 1 by R square into dr. So if you simplify this one, R square is equal to R power minus 2, that becomes your minus of 1 by R you will get. So this can be written as, by substituting, by doing the integration and by substituting it, here finally you are going to get work done is equal to Q by Q dash by 4 pi epsilon 1 by R2 minus 1 by R1. 1 by R2 minus 1 by R1. So this is your final value of your work done. So in the previous case we have written some points. What are all the points? The first point is work done depends only on the initial and final positions. So this is your, this R2 and R1 indicates your initial and final positions, or this R2 and R1 indicates your the distance to the initial and final positions. So the work done only depends upon the initial and final positions of your Q dash, and it does not depend upon the shape of the path taken. So the path may be like this. This may be a P1 or this may be a P2, and this is your Q, and this distance is R1 and this distance becomes R2, and the path may be a straight line. Here you may have Q, here it is of P1, here it is of P2, and this becomes your R1 and this becomes your R2, and path may be of like this also. So this is your P1 and this is your P2 and this is your Q, and this distance is your R1 and this distance is your R2. So distance, irrespective of your path of your P1 to P2, this depends upon only on the distance only, or initial and final positions only, not on the path of P1 to P2. Next, work done is inversely proportional to the permittivity of the medium. Here, W is inversely proportional to the permittivity of the medium. This is your second point. The next point is, if the charge is moved over the closed path, then it means that what do you mean by closed path? If the charge is moved between closed path, for example, this is of closed path. If Q is equal to, if Q is here, if charge is moved from closed path, for example, this is the distance of point P1, the charge is moved like this. If the charge is moved from this point to this point, that is P1 is here, it is started from this here, and P2 also same, the same point. If the charge is moved around the closed path, then R2 and R1 becomes, R2 is equal to R1. R2 becomes R1. Because these are the two are the same points. So hence the work done will be 0. Why? Work done is equal to Q dash by 4 pi epsilon R 1 by R2, that is your R, 1 by R1, that is your R. So 1 minus R minus 1 by R minus 1 by R. This becomes 0. So the work done will be 0. So this is because of energy expended in moving a charge around a closed path becomes equal to the energy supplied by the field. Next, as the energy is conserved field, or it is a static electric field, if the energy is conserved, then the static electric field is also conservative field. What do you mean by it one? This implies that if we are moving over a closed path, so what is the W is equal to? W is equal to generally minus Q into integration over E dot dl. E dot dl. When this W becomes 0, if this integration is becomes 0, that is if you move around the closed path, we have to consider the closed integration. If this closed integration becomes 0, then the work done will be 0. So if this integration becomes 0, then the respective electric field is called as conservative electric field. The respective electric field is called as conservative electric field. Conservative or conservative electric field. Conservative electric field. This property is called as, that is of closed integration of E dot dl. This property is called as conservative property. This property is called as conservative property. So in the next class we are going to see potential difference and absolute potential. After that we are going to see equipotential surfaces. Thank you.